So my attempts to get an 8-bit graphics chip working with my board have proven to be quite unsuccessful. Just like they were last time, I spent quite a bit of time trying to get it to work, and I couldn't get it to work. And so it's either just give up on video or try something crazy. And I decided I would just try something crazy, which is force a Raspberry Pi to be my 8-bit video card. And so this has been kind of a side project for quite a while now. It started out as one side project and then it branched into two different side projects. And each one took quite a bit of time. But they've been fun. They've been fun. I'm not sure how productive they've been, but they have been fun. So there is that. So of course here is a Raspberry Pi 3 B+. We've got just a couple things connected to it right now. The power, of course. I've got network because I need to talk to it. And then that final cable acts as both an audio or video cable. And of course I'm only using the video cable. So let me move to over here, and I've made just a couple of very rudimentary diagrams. Oh boy, and the camera focus is not happy here. There you go, that's a little better. Just kind of laying out how this all works. So basically the 8-bit, the fake 8-bit. So maybe I should back up a little bit. So the primary piece of software is a bunch of code that runs on the Pi. I wrote it in C++. That pretends to be an old school 8-bit video card. And the way that it does that, is kind of laid out here. So basically, all it is, it's really pretty damn simple. All it knows about is a 32K VRAM address range. So it has, according to, as far as it knows, it has 32K of VRAM. And most of that, it doesn't even know or care what's in it, except for these very, very upper portions have a bunch of registers that control the behavior of the video card. And this is pretty common for how these cards would have worked back in the day. So we have 192 bytes worth of registers at the top of VRAM. And out of the 192, like 160 of those are just used for sprite data, and not sprite data, but sprite registers. So things like where on the screen should the sprite be? Should the sprite be enabled? Should the sprite be stretched vertically or horizontally? Things like that. So they're sprite registers, and there's 32 sprites, and so it's like 5 bytes each. And so like 160 of those 192 are just for sprites, and then another 24 bytes out of those 192 is just the color palette. And then that just only leaves like a handful more, and what that handful more control are things like the video mode and how the video RAM gets interpreted. And that brings us to this side over here where it says VRAM allocation. Basically, there are two primary kinds of modes that the graphics card, for want of a better term, can be in. And that is kind of like a text mode and a bitmap mode. The text mode is very, very similar to old school 8-bit graphics chips like the VIC-2 and the Commodore 64, and the TMS 9918 or 9118 that I was going to use in my board also did things in this way. And maybe I can just kind of explain how these text modes work a little bit. The screen is divided into 40 columns, left and right, and then 25 rows up and down. So if you see where I say there, 40 times 25, that's 40 columns, 25 rows. And each cell in that 40 by 25 grid holds 1 byte. And that 1 byte indicates which piece of text or which letter or number or character you want to show in that particular cell. And so, the different companies called this buffer different things. I think the Commodore called it screen memory, if my memory is correct. But in the Texas Instruments documents for the TMS, I think they call it the name map. But anyway, they're the exact same thing. So anyway, 40 times 25 means we need 1,000 bytes to store which letter or number or character to hold in each of those 40 by 25 cells. Then you have a completely different set of memory that is used to actually describe what those text characters look like. Because each text character is actually, how you can see here, is an 8 by 8 pixels by 8 pixels big chunk of data. And so when this part of RAM says, hey, I want the letter A to show up in the upper left corner, we still need this part of RAM to tell us what the letter A looks like. And this is super important, as we will see later in the video, because we can customize our font, and the font is multicolor. So each of these definitions that defines what an A looks like, for example, can actually have many colors in it. And that can let you do really wonderful things in games, because you can make, instead of the letters A, B, C, you have a grass and mountain and tree, right? So you can do stuff like that. And then finally, this RAM down here, sprite memory. The ratio of these sizes is probably not completely accurate. Sprite memory is whatever you have left over. So this is 8K for the font memory and another 1000 for the screen memory. We have 32. We have 32K. So look, we've only used 9K there. All the rest is for sprites. Now you can only show 32 sprites on the screen at one time. And that is the same as the TMS 9918 and 9118 that I was going to use. But you still want to have all of that RAM for your sprites, because even though you can only show 32 on screen at once, you still want to have a lot of frames of animation. Because really what you want to do is when you load your game in, you want to fill up the VRAM at load time and then just never have to touch it again. You don't really want to have to be updating VRAM all the time and blah blah blah. That's not how they did it in the old days, because your CPU cannot move huge amounts of data at a very fast rate. So yeah, you really want to just fill this up with everything, and then run your game. And then as you need these different sprite frames, as your game unfolds, they'll be there. Now, I think I did the math a little while ago, and I think so we got 9K used. We lose a little tiny bit from the registers, but mostly we have the rest of that left. And I think it ends up being 180 frames of sprites. So, if you had 10 different sprites, then you could have 18 frames of animation for each one of those, or whatever combination that you saw appropriate. So that gives you a huge amount of flexibility between. Oh, and this, by the way, the sprites always draw on top of the text, which is really, really important and good. Because you use like the text becomes kind of like the background, and then the sprites that get drawn on top become like the foreground where the action is, and those are animating and moving around the screen and all that, and it all makes sense. Okay, anyway, so back to the whole big picture. That's like the text mode allocation. We've got oodles of RAM for this mode, tons of frames of animations for our sprites, lots of colors, everything's great. This other mode is like bitmap mode. And in this mode, no text, no fonts, pretty much no sprites. They are still supported, but as you'll see, we'll have no RAM for them. Because when you're in bitmap mode, 32,000 bytes are needed to actually display the screen. And this is really like you could not make a game in this mode. Like the poor 8-bit CPU could never move that kind of amount of bytes around, or even a subset, like not even like a quarter of that. So really, this mode is for more dry things. Oh, okay. Well, it is for like title screens. So like if your game was going to have a title screen and you wanted something with a lot of color and really fancy and looks really good, then you could use this bitmap mode. You could load in 32 kilobytes from, tape or wherever you're getting the data, and then dump it directly into VRAM. Don't even store it into your main memory. Just load it from tape directly into VRAM to show your title screen. And then after that's done, then go start actually loading the real game. And then they can look at the title screen while you're doing that. So there is that. But then the other mode where this might come in handy would be things like, a paint program or something like that. So, yeah, it seemed a shame to me to not have that mode, because if you didn't have that mode, then even though how flexible this old school 1980s, how we did graphics in the old days format is really great, but if you didn't have this mode, then you literally would not have any way to individually color every single pixel on the screen. And that's kind of limiting. So I thought it was important to also have this bitmap mode, even though, not going to be used that much. Okay, so now I'm almost done with all this exposition. Let's briefly cover what modes there are. There's only 4. You can see. They're grouped in sets of 2. So the first 2, let's start with mode 3. The first 2 are both black and white, and only 2 color, and they're high resolution. And the Atari ST had this, and I thought that was always really cool, because sometimes your game would benefit from being in higher res, even if it was only black and white. There are cases where that's true. So I thought that was really cool. So we have that. We have the bitmap mode version, if you remember over here, bitmap mode version of black and white. And we have the text and sprite mode version of black and white, which is fun. And we will see all of this in just a minute. Now, then we have mode 1 and 0. And this is the bitmap mode of color and the text/sprite mode of color. And of course, that's only at 320 by 200 resolution. And of course, mode 0, by far the most useful, common, helpful mode for video games. Okay, so without further ado, and actually there is going to be a lot more ado, but without too much further ado, let us move to the actual demo. So let me pull up. Let me pull up. I've got a couple shells into the Pi. And in fact, I already have my test program running. And it is currently showing us a demo of mode 3. So this is the black and white only 640 by 400 bitmap mode. And I just have this little picture that I think I got off the internet and threw into GIMP or something, and it's like 1 bit per pixel, literally 1 bit per pixel. So yeah, so that's that. And now let us move to, we're going to go to the next mode here, which is going to be mode 2. So this is, again, black and white, 640 by 400, text and sprite mode. In this mode, the text, it does not support scrolling text, but it is 80 column, which is pretty nice. So if you had like an Infocom game or a Zort game, and or like a menu-based game, like a space trading game, and then you could use the 80 columnness and high resness for most of your text, but you still have these sprites floating around where you could maybe, have in the corner of your screen some little small animated battles or something like that. Anyway, the memory allocation that I showed over here, and I showed like 8K and 1K, they're slightly different for the high res modes, but not that different because it's only black and white instead of 16 colors, so it kind of all just balances out. So let me go back over here. And now it's going to get interesting. So now we're going to move to the mode 1 test. I'm just going to hit N and hit enter. And now I have to hold this phone up for a while. So I mentioned that making the Raspberry Pi my video card was a side project, and that I then undertook a second side project after the first side project. And the second side project started after I finished mode 1, and I wanted to run some tests on it to make sure that it was working properly. And so how do I do that? Well, I do that by, having a 16 color image that I can show. Well, I wanted a good looking 16 color image, but, most of the images that you get off the internet and whatever are high color, true color. And I thought it would be a fun challenge to try to do some color quantizing work. It's actually quite a difficult problem. And you can see kind of the result of many weeks of work happening very slowly before you as the Raspberry Pi is slowly but surely desperately searching for the best possible color to use to improve the image. Now, if I was like a math genius, then I would have solved this the correct way, which is you solve for all 16 colors simultaneously, because the colors interact, because you can see there's dithering. It's blending the colors together to try to invent extra colors, because we're a little low. We're a little short on the number of colors we've got. So ideally, you would solve for all 16 simultaneously, and then you could kind of guarantee the best possible color palette that blended in the most ways that were the most helpful to create your image. That's like really high level linear algebra or some crap. I can't do that. So I have to pick best colors one at a time. So I wrote a function that calculates how much error there is from a certain palette against a certain, true color image. And then I wrote a bunch of code to try to find a way to minimize that error. And, well, it's been really fun. It's been challenging, but it's been rewarding. One thing, what keeps happening is that I'll find a way to improve, say, the color picker, but it'll slow down everything by like 4 times. And then I'll spend a few days just trying to get it back up to speed to where it was. And then I'll go and I'll be like, oh, there's this other dithering pattern I could use. And then I'll slow it down another 2 times. And then I have to go and try to get my speed back again. And so, and then I had made it multi-threaded in order to try to squeeze more speed. So this is actually 4 threads running on the Pi to try to speed this up a little bit. Let's see where we're at. Oh, we're at number 13 out of 16. So we're getting there. It's still going to improve a little bit. So yeah, I know this is a long one. This is a long one. I knew it would be. And, I considered like, oh, maybe I should work on the algorithm more. Maybe I should spend some more time on it. I bet I can get it faster. I started to do a little bit of profiling on it because this is just C++ code written against SDL. It runs on both Pi and my Windows machine. So I can run this on Windows and I can do like profiling of it and stuff like that. But it's already been I've already been meaning to make this video for like a week at least, if not 2. So I'm just going to make the video because I have done a lot of work here. And, hopefully I can just put all of this color quantization stuff behind me and just move on with the project. But there are still some aspects of it that I can't help but find interesting. I'm sorry for the shaky cam. I'm having to hold it. There are still some aspects of it that I find really interesting. There's still a couple more dithering patterns that I find interesting. So I might spend a little bit more time on it, but probably not too much, because I've already spent a lot. And also, I know for a fact that I'm already really close to having it to be the best that I personally can get it. Okay, so here is our original image. That's the real deal. I thought that was a nice looking image. I tend to like the images that have a lot of the oranges and reds and browns. That tends to be the ones that I kind of like. And so there is our 320 by 200 16 color dithered attempt at that same image. So, we do what we can, right? We do what we can. Okay, so that was really long. Let's go back to here and let's do our final test. We'll do next over to mode 0. And here we have mode 0, and it's a circus. Now, you have to kind of use your imagination, because I didn't actually, write a game and make a bunch of art. But you have to imagine that all those characters, all those text characters in the background, could be forest and mountain and grassland, or battleship and water and, just whatever. And then it stopped. It automatically stops after 30 seconds. And then all the sprites that are tumbling around on top can be fighter jets or spaceships or, whatever. Man on horseback. You have to use your imagination, but you could see that mode in action, and that's what it can do. And that is really enough for an old school 8-bit game. That's really all you need. And now my voice is absolutely going out, so I am going to call it a video here. And if you're still with me, thanks for hanging in there. Bye-bye.